So this density matrix approach makes it very easy, for example, to express the expectation value of spin in a certain direction. So in terms of the C1, CI daggers, CJ comp product that we defined rho 1, 2, in terms of those, you can obtain differential equation for each one, and so in class we went through each one of these time derivatives of each one of these expectation values, and we expressed them in just the expectation value of the spin in some other direction. So for example, Sx depends on Sy, there's a mistake. Sz depends on, this is X, Y, and Z here.
There is one term missing in the middle row, but
for the expectation value of S sub Z.
But do not worry, just present concepts and.
Okay, so the time derivative of Sx, Xy, and Z can be expressed in just the expectation value of Sx, Sy, and Z. So in this formalism, the time dependence of the total vector, the length of the total spin vector is zero. That means it's constant. That means on the Bloch sphere, the tip of the total spin projection will always lie on the surface of the sphere. So there is no relaxation, which we need in order to describe NMR, because in NMR, as we know, the total magnetization, which is proportional to this quantity, eventually comes to zero. So what we need to do is we need to introduce extra terms in each one of the equations. Indices are wrong again, sorry about that. But for each equation, for each expectation value, you just need to add, or in this case, we subtract a term. At this point, these terms were phenomenological. So depending on what T1 and T2 is, will tell us how fast the total spin vector will relax as a function of time. So the T1, the one that multiplies the Z projection, we call it a transverse relaxation, and the other one longitudinal relaxation.